Okay, so now we're going to talk about the capacity of a neuron, or of a single neuron first, then, because we'll start out with the single neuron. And capacity means what kinds of functions can we model using this. And we're talking about here when we have a sigmoid function. So we said that we can put all kinds of different functions into a neural as the activation function, but we're going to talk specifically here about a sigmoid function. So if you remember, a sigmoid function is always between 0 and 1. So no matter what input you give it, it gives you a number between 0 and 1. And that means that you could treat that number as a probability, because if the number is between 0 and 1, it can be thought of as a probability. So if it's a half, we'd say the probability is 50%. If it's 3/4, we'd say the probability is 75%, and so on. So we could consider the output as modeling a probability. Now, just to make this a little bit clear, the first time you run the data through the neural network, or through one neuron, for example, we're going to get some number, again, between 0 and 1, and that's going to be the probability that something is in class 1, or in one of two classes, but there's no reason to believe that it's going to be an accurate prediction of the probability. It's just going to be like a wild random guess of the probability. But then we're going to train, we're going to say, okay, well, the neural network guessed that the probability was 3/4, that it was let's say we're trying to decide between something is sweet or not sweet. So you guessed that it was sweet, but you were wrong. So what do we do then? We train the neural network. We go back and adjust the weights so that it might give a different prediction the next time. So just to make that clear. Anyway, so with a sigmoid function, we can interpret the output of the neuron, the activation, as estimating the probability that the output is 1 given x. This is the conditional probability that y is equal to 1. That means like 1 or 0, like yes or no, or sweet or sour, given the input vector. So when we say the probability that y is 1, we're assuming like 1 stands for sweet and 0 stands for not sweet or sour or something like that. Anyway, we're just saying that y is going to either be 1 or 0, and we're estimating the probability that y is 1, or it could be y is 0. But anyway, we're going to train it based on this. So since we're using the sigmoid curve, or this is exactly, this would model exactly, or this would be exactly a logistic regression model, or logistic regression classifier. And we could use a cutoff, say, of 0.5 here. So if it's greater than 0.5, we'll predict class 1, and otherwise we'll predict class 0. Or the cutoff doesn't have to be 0.5, but we choose some value. And if it's above that, it's class 1, and otherwise it's class 0. And here, this is basically the surface here. So what we're saying is, now actually I can't tell if this is a picture of a sigmoid or just a perfect jump, a step function. But let's say it's sigmoid, so it's kind of more, there's a little bit more of a curve here. So what we're saying is, I can't really draw this because it's two-dimensional. I want to do 3 dimensions. But if you imagine like a plane that is parallel to the x1, x2 axis and of height, say, 0 right here, so you imagine that plane. So what we're saying is whenever the function is above that, we'll predict class 1, and whenever it's below that, we'll predict class 0. So what that turns out to look like is this. The area where it's going to be like below might be this area. So that would be the area where we predict 0, and this might be the area where we predict 1. And this would be called the decision boundary, because in this region, we're going to predict one thing like 0, and in this boundary, we're going to predict something else, say 1. And it turns out that the sigmoid function generates a perfectly linear decision boundary. Now, we talked about linear before, but we weren't talking about linear decision boundary. We were talking about the activation function being linear. That's completely different. Now we're talking about the activation function being a sigmoid function, and the decision boundary that it generates is linear. So what it means is, if we use a logistic regression as the activation function, and we have just one neuron, just one unit here, just one node here, that we can only create linear decision boundaries. So if I wanted a more complicated decision boundary, like from here to here would be one thing, and from here to here would be something else, and from here to here would be something else, I can't do it with this, with one neuron and with a logistic activation function. But I can, and I will, produce this linear situation here. So we get this line like that. Okay? And actually, tan H will also give a kind of a similar shape. So remember that at the beginning of this video, we said, well, what kinds of functions can we model? What kinds of classifier functions can we model? And here we see that we can model only, using this configuration, we're using a logistic function and just one neuron, we can only model a linear decision boundary. So that's not that flexible. For example, if I wanted to model something like this, where, like in this white region, I'd predict, in other words, if x1 had x1 and x2 had inputs like around here, then I'd predict R1. Or if they had inputs around here, I'd predict R1, but otherwise I'd predict R2 and R2. I can't model this kind of decision boundary or this kind of classifier with what we've seen so far. Okay, so next let's take a look at this kinds of data and see how it compares with what we want to model. Or I'm sorry, rather what we can model.